Okay, cool. So let's try it again. Now, this side of the room, please close your eyes. So the right side of my right side, please close your eyes for a second here, okay? You guys, I want you to pay attention to this. Got it? Okay, all of you, close your eyes. This side of the room, close your eyes. You guys on my right that first closed your eyes open, you're going to pay attention to this. And no cheating on the left over here? Got it? Okay. Everybody open your eyes. Let's watch again. So by doing what I just did, I'm controlling your attention. And we're going to see how this works out now. Yeah, I love Psych 101. Okay. So that's it. I know it's really dramatic, right? So raise your hand if you saw this building get entirely replaced. So raise your hand if you had buildings as your assignment. You didn't see that change? Okay, watch. Yeah, that's what it did. Yeah, that's what it did. And also, by the way, the people disappeared. Did you know who noticed the people disappear in the original? Yeah, look, this half of the room, right? One person on this side. Attention is the modulator of the traffic cop of perception, and that's the point here. So, and I think William James, who was a great American psychologist, said it better than anybody else. So this is a great quote, and basically it's the point that to deal with all these simultaneous, multitasking, simultaneous thoughts we have, to put our focus on one, we use attention. And he wasn't talking about overt attention, moving your eyes around. We just saw that, and moving your eyes around doesn't help. We're talking about covert attention, which is moving your mind's eye. And we're trying to understand that here. So I promised some brain decoding and an understanding of your thinking, which starts with attention, because if we don't understand where the flashlight of the mind is sending us, whether it's looking at memory or doing comparisons or doing analytical work, we really can't understand thinking. So let's start by understanding attention. And that's what this shows here. So when I talk about perception, like seeing things with the eyes and processing with the visual cortex, that's what you're doing right here with this grass. It's a wonderful video, isn't it? Grass is a wonderful thing. It's good for the whole planet. So, of course, I'm getting awkward here, that's interesting. So, depending on how your brain processes those perceptions, those turn into memories, they turn into thoughts, you do an analysis, and things like that, maybe your agricultural science. And that's learning, and that's regulated by that attention that I talked about there. The real challenge with this type of research, like understanding how the mind arises in the brain, is the brain itself, this giant black box at the end of our necks. And it's amazing. It's an amazing organ. It's probably the most complex system, well, it's the most complex known system in the universe. And it uses up to 20% of our energy, even though it weighs 2% of our body weight on average. And the interesting mammalian brain, or the higher thinking that we do with the neocortex here, is, as I said, extremely complex. So it's going to take some really interesting analysis to understand the patterns in the brain if we had a way to look into it. We can take I've been working on data science tooling. We can take a workflow approach to the problem. If we had some kind of task or stimulus like I gave you at the beginning, and we could run that through the mind and the brain, the anatomical brain, and underlying neurons that the mind arises out of, and we had a data set for that, we could process this. We could try some tricks with it. Maybe we could try to figure out what is present in the mind as the task is performed, and come up with a computational model. So the challenge really is, what's the data set here, and how can we develop a computational model of not the overall thing, but the mind itself. And I can reduce this down initially to the task of trying to figure out what is attended to in the mind as a task is performed, as one step towards understanding thought. So, about that data set. Well, there are many ways to study it. When you're dealing with organisms on the planet, there are many non-invasive ways and non-invasive ways. With human subjects, you try to stick to the non-invasive methods. Some of them have better spatial and temporal resolution than others. One that has a really good set of trade-offs is called functional magnetic resonance imaging. How many of you had an MRI before? So the kind I'm talking about here is very different. We can actually see metabolic activity and even over time. And so we can study the metabolic activity with resolution over the brain. And fMRI has become the workhorse for this kind of cutting-edge research because of its characteristics, even though it's quite cumbersomely tons and costing a ton of money as well. But what you get out of an MRI is time series data. This is 4-dimensional data. We work in elements of voxels. Those are 3-dimensional equivalent of a pixel. And you can see that there's a metabolic brain and an anatomical brain. So when you get a standard MRI, you get an anatomical image. If you change it to look at blood oxygen levels, which are an indicator of neural activity, you can do a contrast imaging on that, and you end up capturing the metabolic brain at the voxel level over time. And so those are the patterns we're interested in. That's the patterns that we could potentially classify and do interesting things with. And so now that we have that idea, we can take this real-time fMRI data, and we could do a classifier potentially that looks at those patterns over those voxels over time, and we can label tasks, and we can do all kinds of interesting traditional machine learning on that data. And from the brain, we can draw conclusions from the feature choice that we take. So where the voxels are activated, how they behave over time as someone's put under a trial. That'll be very dependent on the experiment. We can see that, we can observe that, we can understand what part of the brain is related to that type of task, visual processing and breathing and other things like that, clearly. About the mind, if we had an ability to do model-based machine learning, to build a model of the brain based on our understanding of it, we would learn something about the mind from looking at the hidden, the weights on features, the weights on correlations that are happening in the brain, connectivity, the hidden layers that exist. And obviously that's going to depend on the prediction model that we make if we're doing a prediction type thing. We're trying to predict the task that's going on from just this data, or trying to predict data given the task. Okay, so back to attention. So the question is, what's the simplest attentional experiment we can do to kind of explore that kind of pipeline, that kind of analysis? And I think you'd agree it's probably if we look at how your attention may be divided between two things. Have you ever had that happen to you? So here's a good example. We take an image, it's half face, it's half scene. And by looking at you, I can't really tell by looking at your eyes and the attention you're paying right now, like which of these you're paying attention to. Is your mind on face, or is your mind on scene? The good news is there are actually anatomical areas of the visual cortex that are specialized at facial recognition and environmental recognition, pattern recognition, a fusiform face and the parahippocampal place area. Amazing. I didn't know this before I started this work. But if you look at the anatomical brain, you can actually map those two things out. So if I stuck a big probe in your head and destroy them, you might not be able to recognize faces, even though you can see it with your eyes and process the information. You wouldn't recognize the face. So we can look at the activity in these two areas and determine, in some way, hopefully, whether you're paying attention to the face or paying attention to the scene. And like I mentioned, the blood oxygen level of this BOLD is what it's called. These blood oxygen dependent levels in the brain are what we can use to do that. But it's not as simple as just looking at whether the area is activated. So is the place area, you're focusing on the environment, is it activated? That would be the blue level higher, using more oxygen with those neurons. That's not changing here though. You can see in the two scenarios. The other area is changing. These areas are modulating each other though, and that's the thing we can look at. So the interesting thing that was discovered fairly recently is that there are these hidden brain network pathways, regions of the brain that are quite separated can be interacting and suppressing each other. So we can actually look at, there's a hierarchical organization in the visual cortex where low-level features like the ability for you to discern vertical lines and horizontal lines is processed there. And then that can be used by centers that process faces and environments out of those primitives. And so by looking at how those things are interacting and how they're correlated, the correlation between that area V4 there and these two other regions that are specialized, then we can understand what you're really paying attention to. And you can see that in this graph, where it's so easy before to maybe use a classifier to separate the two based on just their activity levels. You can see very clearly here that when you're relative activity in these two regions, when we look at the correlation with V4, they flip. So we can clearly see the brain on face and the brain on scene. Okay, so understanding that, the question is, it's looking not so bad. I thought it was going to be completely mutilated. But we can sort of build on the underpinnings of standard fMRI analysis to sort of construct a classification experiment here for attention. And so just walking sort of the levels of that type of analysis, first of all, you can look at just single activity areas in the brain, and that's called univariate activation analysis. It's been done for a long time. You can look at patterns of activation across regions that you mask on the brain. So I'm looking at just the visual cortex, for example. And you can look at those patterns and put labels on them and divide the hyperspace that way. You can also, but we're also, as I mentioned, interested in connectivity. So we can look at the correlation between one activity area over time and any other voxel in this brain study. And we can do that also for over different conditions and over the whole brain. This is a full correlation matrix, for example, over the whole brain. And those more advanced analyses are the ones that are interesting. You could run those, and then you could potentially run an SVM classifier and come up with some pretty accurate classification for an experiment like that. So this is multivariate pattern analysis, and then this other type that takes into account connectivity is called full correlation matrix analysis. And so the way you construct a pipeline, a processing pipeline for that, is you put someone into the scanner, you do a bunch of pre-processing, which is really important to get the image quality right. So you can do spatial and temporal smoothing and registration, aligning the anatomical brain to the metabolic brain. And then we can do that type of voxel analysis that I talked about, MVPA or FCMA, and then ultimately run a classifier and then analyze the results offline. So this is the type of thing that's happening now in Oxford and Princeton and these cutting edge neuroscience institutes of the world. But what we're interested in doing with our partners is real-time brain decoding for causal experimentation, because it's one thing to kind of prove that there's some correlation with something going on in an experiment, and it's totally another thing to actually be able to control the experiment in real time and change the way you're interacting with the subject based on what they're doing, what you're seeing in the brain, to prove that you're causing that activity, and to also use it for therapeutic purposes. So can we train people to improve their attention? Well, we have these attention games. They're really based on some of that univariate and other types of analysis that we've talked about. And the question is whether we can really, for people that have lock-in syndrome and can't even communicate, can we see what's going on in their head with a classifier and know what they're thinking about, or whether they're thinking, and so on. These are really important questions. And so if we go back to studying attention, if we were to create a real-time neurofeedback pipeline, it would look, or experiment, it may look like this. So let's construct this experiment, maybe I'll show it to you. So if I asked you to attend to seeing, when I was showing you that dual image, I'd start by showing you maybe something 50-50 here. That's the starting stimulus. Now, in this neurofeedback, what I'd like to do to train your attention the way I want you to pay attention is obviously I have a trained classifier, so I know what's going on. So I can tell if you're looking at scene or face. Let's assume that up front. And then if there's more scene evidence and the classifier is saying, yeah, I'm very confident that they're thinking about scene, then I'm going to reward you by showing you more scene. And so you can see the face is faded, and there's more scene in this image. On the other hand, if you're not paying attention, you're not doing what I'm asking you to, I'm going to punish you. And I'm going to show you more face, and you're going to have to work harder to pick out that scene out of this. Maybe I'll leave a little bit of scene in there so you can bootstrap yourself back and hopefully go the other direction and pay attention. And so this is a really simple experiment, but there are many that have been imagined by neuroscientists. And what we're trying to do at Intel is help them realize these massive numbers of experiments that they have in mind that they can't do today because they don't have the real-time capability to see if these things are true, to prove their hypotheses out. Oh yeah, there's the punch part. Okay, so it's a very small modification of the pipeline, but the real challenges for us as computer scientists are, because I'm definitely not a neuroscientist, are to turn this preprocessing into a real-time version of it that scales up with the size of the subject data, which can be quite significant, and the type of processing we're doing, and to do real-time voxel analysis like FCMA, and run the classifier on it, which is usually not a problem. Training it is a different thing. And then to provide that feedback to someone that's in the MRI, so maybe to project it onto a screen, that particular image I showed you, and talk to them through a microphone and instruct them. Right? So we're talking about literally giving them real-time neurofeedback. So the way you design that is maybe you train them by looking at a series of faces and scenes. So I just say, just pay attention to this face, pay attention to the scene. We do that for tens of those. We train the classifier because I'm getting the metabolic, brain activity out of that. Thank you. And then after we have that fixed, we've got this series of images that we're collecting. We have the classifier trained, and then we can provide the neurofeedback and see if if this is accurate. By running like MPPA to do that, for example, then I can do that. And actually, the numbers have gotten better. This is where they started. I mean, this is probably 75% is kind of the low range of what is therapeutically or clinically interesting, let's say. But we're going to 95% ranges with these classifiers. And so we actually put one of our researchers into a scanner a few weeks ago. It's a little bit intimidating. They have this thing, they have to have mirrors so you can see the screen, and your head is held there with a receiver coil that's capturing the signals of interest here and laid really, really still. Because otherwise we have to register over time your image as it moves, which is a whole other problem. Now I'm going to show you the actual video clip I took on this iPhone here of how they did on this experiment that I just described, where we're going to ask them to pay attention to scenes and see how well they do. So this is the first time, I was amazed, this is the first time I've ever actually seen mind reading in practice. We've all heard about it, so I guess I'll share it with you via video today. Let's see if it works here. So there's the neutral, right? That's 50-50 at the beginning of the experiment. He's in the scanner in the other room. Uh-oh. It's suddenly all faces. But there's a little bit, you can see a little bit of scene back there if you look carefully. And so we tell them to keep trying. You see it changing? So every time a new image came up, that's how fast the machine is spitting out a full scan of the brain. That's a lot of data. And you can see that it's interesting. The classifier actually worked. This is exactly what, if you then interview the subject and ask them what they were thinking about, this is what they'll describe they were thinking, and there are different ways to verify that as well. So I just think it's an amazing possibilities. So that was done with MVPA, but we're ramping up to do this full correlation that takes into account connectivities across the brain as well. And as I mentioned, though, it's a big challenge. It's a large amount of data. You can collect 0.5 terabyte on a subject for a short study, and then you have to process all that all the way through that pipeline to extract all of these calculations you want to do for both the pre-processing and the full correlation matrix. And the idea is that we want to allow scientists to be able to update their research as they have someone in a machine. The time is very expensive. It's hard to get people into those machines and set up. So if we could have them go get a cup of coffee and change the experiment, that'd be great. That means we have to run a full multi-subject test set through, because we train this across, we train the decoder on many people to get a generic decoder, and then we specialize it to the person. And then when we have the person in there, we obviously have to keep up with the rate coming out of the machine. And so Intel, anyway, is focused on these building blocks. To help with that, my team is applying techniques at the level of high-level primitives and low-level libraries. I'll talk a little bit about that here. How many of you use the math kernel library and know it's even there? It might be used by your code and you're not even aware of it. So this audience would be particularly interested in sparse, linear, and dense linear solvers that are used for matrix computations and accelerates a lot of the stuff we do. And we're applying it left and right in this pipeline. Also, the fact that Intel's got a brand new version of Xeon Phi accelerator coming out the second half of this year is available, is going to just totally change the game, because this is socket-based. This is not across PCI Express. You don't have these data transfer overheads, and it's going to, for highly, massively parallel computations like this, we can set up a cluster of these, and it can do amazing processing. So it's really important to optimize the code. We've already done this with the full FCMA, and we're running the new experiment on it. But so we have over 500 million pairs of correlations to run every time we get subject data. But by doing some clever things, you can use MKL quite well to do it. So you can turn the Pearson correlation into a simple matrix multiplication through proper adjustment of the mean and the variance normalization. And then we can apply the matrix multiplication library built in Intel math kernel and get it to run a lot faster. So we did that. We also used the natural log accelerator to do the Fisher transformation for the z-score, which is a hyperbolic arctangent computation. And we vectorized everything so that we're taking in and processing voxels using a vectorization technique over time and over space. And you can see that the way that code is written, if you're writing C and you want to do this yourself, is you just add these pragma statements that allow for the parallelization to be picked up and the libraries to be used. And so in this case, we're using a Xeon Phi and distributing dimensions of that data set over the cores and over the threads in the Phi. Yeah, I know I'm out of time. I'll try to catch up here. So we can do, there's also optimizations available for the SVM classifier that we used in this case, and getting single instruction multiple data parallelization for that. So you should try it if you're using these and you need faster classifiers or correlation or any matrix operations. You should really look at that, or reach out to me and we'll help you out. That's what our team specializes in. And so even just the early work on the FCMA pipeline, you can see we need to get under a second. The total pipeline through the correlation, z-scoring, and the SVM steps is now at about a second. And we started at one that was highly optimized. We had already been working on it quite a bit, and it started at 6 seconds. So we're getting there. We're going to put it into experiment now. And then finally, I just want to say that the ultimate goal, though, is not to run a classifier over the whole path that I talked about there. It's to isolate the mind itself and to discover what the model of the mind really is. So if we look at that, we want to see if we can build a model that uses the brain information, the low-level voxel information from the MRI data, and understanding an anatomical brain to predict tasks and turn that around and predict the data and prove that we have good models. And so a model like that might look like this, where over an experiment, different parts of the brain get activated over time, and we learn what the network representation is of the brain doing different types of tasks from the way those hidden sources in the brain interact. For example, maybe your brain is on animals, so we ask you to think about any type of animal, and there's a common network of activation for that, and for insects, and for tools, and for vehicles. You can imagine applying the entire knowledge graph to this and mapping it here and exploring the relationship to really decode the brain. And so this is a new technique we're also optimizing and working on right now, the topographic factor analysis. We're hoping it'll be one of our first attempts at doing a model-based approach to this type of research. And I don't have time to go into it, but basically you hide a bunch of Gaussian sources and you learn where they're located and how they correlate with each other and what their widths are and so on. And that's how you build the model here. And so there are a lot of questions that are open about models. There are a lot of hyperparameters. There are a lot of fundamental questions for TFA here in terms of the number of sources you pick and how you initialize. And they all have big impacts on it. So it's a work in progress for sure. But if we're able to succeed with it, with TFA, then we may be able to build a joint model like this, which shows the relationship between a given mental state of the subject out of a set of possible states and the behavioral that arises, and correlating that with the, I don't mean correlation in a strict sense here, with the activity you get out of the image data. And so this is kind of the grand vision here of being able to describe mental states and tie them to both ends. So like I said, work in progress, lots of basic neuroscience research that will be advanced by this work. A big need for faster machine learning and more accuracy. If you have any ideas, please reach out. And stay tuned for the model-based approaches and maybe some publications in top journals on both sides. So I think you can see that it's very difficult to access the inner states of the mind, and that's what this work's about. But I think it holds a lot of promise for a lot of reasons, both clinically and for just simple brain performance improvement. And we're going to help unlock that by bringing real time to it. Thank you.